Hello and welcome to this MOOC video. My name is Thorsten Hüffer. I'm an environmental chemist and senior scientist here at the University of Vienna.
Hello, my name is Anja Schürmann. I'm a PhD student working in environmental chemistry at the University of Vienna.
This video is about chemicals in the environment and regulatory frameworks of assessing their environmental impact.
We would like to start by telling you a story. In 1874, a Viennese chemist created a new chemical, which was later discovered to be poisonous to insects. In the mid-1900s, this chemical, named DDT, was used widely and had amazing consequences in reducing malaria outbreaks around the world. Then DDT started to be used in agriculture to kill crop-eating insects. Today, I will tell you the story of one molecule of DDT. This molecule of DDT was applied to a cornfield. Due to its chemical structure, DDT sticks well to organic matter, and therefore stuck to a soil particle once it had landed on the field. DDT is a very stable molecule, which means its chemical structure does not change easily. Therefore, when it began to rain 2 weeks later, this DDT molecule was still sitting in the cornfield stuck to the soil particle. As the rain intensified, water began to flow out of the cornfield and into a nearby stream, eventually carrying our soil particle with the DDT molecule with it. The soil particle was carried several hundred meters downstream before settling to the bottom. In this stream, baby fish had just hatched who eat algae and other organic matter from the bottom of streams. One baby fish ate the soil particle containing the DDT molecule, and after digestion, the same chemical properties that caused DDT to stick to the soil particle caused DDT to stick in the fat tissues of the salmon. As the salmon grew throughout the summer, the DDT molecule remained in its fat tissues untransformed. Later in the summer, the salmon was eaten by an eagle, and the DDT molecule again, after being digested, stuck in the fat tissues of the eagle. Over the course of 3 summers, this eagle ate many fish who had eaten contaminated sediment, and DDT molecules started to accumulate in her fat. In the 3rd summer, the eagle's eggs did not hatch. This is because DDT is an endocrine disruptor. Our body has many chemical hormones which act as signals triggering biological responses. Endocrine disruptors are chemicals which can interfere with this signaling. For example, some chemicals have structures similar enough to chemical hormones that they can signal biological responses when they should not actually occur.
But how can we get our hands on if chemicals can be harmful in the environment? A crucial first step at ensuring chemical safety is the PBT framework. It is a cornerstone of the European Union's chemical regulation REACH. Let's look at what the letters in PBT stand for. P stands for persistence and assesses how long a compound takes to degrade. In the environment, this is done by microbes or other chemical processes. If a chemical lasts longer than a certain amount of time in water or soil, it is persistent. The B criterion assesses whether our chemical can build up in living things. This is more complex. It means that inside an organism, a chemical builds up because it is not broken down or excreted fast enough. These chemicals can build up to levels that harm the organisms. Finally, the T criterion stands for toxicity. It relies on acute and chronic testing for aquatic species. If any measured toxicity exceeds the defined threshold, the chemical is considered T. The idea is that chemicals that last a long time in the environment can build up in living things are a concern because we don't know what the long-term effects will be. Once they are in the environment, it's hard to get rid of them, even if we stop using them. It is especially hard to protect areas that are not affected by human activity from these substances, as they can move into these areas over time. However, DDT is just one chemical, and we use hundreds of thousands of others. The agricultural sector is under pressure to be more productive. Pesticides are used a lot, and new ones are needed for new pests. Plastics are used a lot and contain a lot of chemicals. Many chemicals are used in industry. Pharmaceuticals are used for humans and animals.
Now, we would like to talk to you about a more current story, about a group of chemicals named PFAS. These chemicals consist of chains of carbon atoms bound with fluorine atoms, with a head, often containing oxygen and or sulfur atoms. The very different head and tail of the molecule mean that different parts of the PFAS have different chemical properties. The tail repels water, while the head repels oils and fats. Additionally, the carbon-fluorine chemical bond is one of the strongest bonds in organic chemistry, meaning that even at high temperatures or other intense conditions, the PFAS structure remains intact. These properties lead to PFAS use in many products, from rain jackets to nonstick pans to firefighting foams. Unfortunately, PFAS is a serious carcinogen. This was actually known by the company that discovered PFAS, but since it was discovered before most chemical regulations, they were able to keep this information hidden. With that, we would like to tell you the story of a PFAS molecule. A new student beginning their bachelor's at the University of Vienna moved into a shared flat in the 9th district and went to IKEA to buy some new kitchen supplies, including a nice new non-stick pan. After watching a lecture, the student cooked some dinner and then washed the dishes. While cleaning the pan, a PFAS molecule was released from the non-stick coating and washed down the drain. This PFAS molecule was transported through Vienna's sewer system and eventually reached the wastewater treatment plant at the southeast end of the city. Here, the PFAS molecule passed through all steps of the wastewater treatment process, including exposure to very active bacterial communities, which degrade a lot of the organic matter in wastewater. However, the stability of PFAS, due to the strong carbon-fluorine bond, meant that none of the wastewater treatment processes had any effect on this PFAS molecule, and it eventually reached the end of the wastewater treatment process, where it was discharged into the river Danube. In the Danube, PFAS behaved differently to DDT. It did not stick to soil particles and sink to the bottom, but remained in the water. This is due to the different chemical structures of PFAS and DDT. PFAS traveled all the way through the Danube to the Black Sea. Here, PFAS remained stable and over the course of several months traveled through the Black Sea, then the Mediterranean, and eventually reached the Atlantic Ocean. Approximately 1 year after the molecule had been first washed down the drain in Vienna, this PFAS molecule reached a distant island in the Atlantic Ocean. Due to the stability of PFAS molecules and their mobility, they have reached every corner of the Earth. In fact, it is estimated that every single human on Earth has traces of PFAS in their bloodstreams.
New technology has improved how we measure contaminants. We now can measure chemicals at very low levels. These new substances don't build up in the environment. But we soon realized that the barriers we have in the water cycle for wastewater and drinking water treatment are not as effective. These chemicals are also mobile. They can spread in groundwater and contaminate drinking water. PFAS are just one example. They can spread from contaminated soil to drinking water, decades to centuries after restrictions are put in place. The European Commission is introducing new hazard classes for persistent, mobile, and toxic substances with its chemical regulations. In both chemical stories, we discussed that these chemicals can be transported into environments where they were not intended. Chemicals are really a problem when they accumulate and affect organisms in unintended environments. This is a new idea in our field, that chemicals can be designed for stability under the conditions of the intended environment, but degrade under conditions of other environments. Now we are in the same situation with PFAS as we were with DDT 80 years ago. Regulation is reactive, not proactive. We have to wait for large amounts of a chemical to accumulate in the environment before we notice toxic effects. Bird population decline, increase in human cancer rates. New regulations from the European Union aim to regulate more safely. Chemicals must be registered in all their uses. Tests for persistence, mobility, bioaccumulation, and toxicity before a chemical can be produced. We want you to understand the complexity of the environmental impact of chemical pollution.
And we hope you have a better idea of both the regulatory and scientific solutions to address this problem.